Right, good morning. Please let us begin. So I prepared two sets of lecture notes today because my anticipation is that we will cover the material in this lecture 20, in good time, and then I want to make use of the fact that you've kindly come here this morning to start to cover further ground, but this may be wishful thinking. Let's see how we go. So we spent a lot of time talking about elliptical orbits. Let's now talk about open orbits. So to be clear, if I draw yet again our effective potential, we've dealt with circular and we've dealt with elliptical. I now want to consider this regime here, which turns out to be hyperbolic orbits, which are, of course, unbound. Now, there's a special case in between, which is just here, which is parabolic, also unbound. But this is really a special case of the hyperbolic. Okay, so this is so here we just draw hyperbolas. So this is, again, we have two foci here and here, but the orbit, rather than going around there, is in this direction. And you have the possibility of one here also. So just to remind you of our key equation, so our orbit equation, which is that r theta is equal to r0 over 1 plus e cosine theta. So for a hyperbola, we are dealing with the case where the eccentricity is greater than 1. There's another way to, I mean, there's various ways to write these functions. We can also write it as x over a squared minus y over b squared equals 1, which is to be compared with the ellipse equation in the same form, which is, this is the ellipse case. We won't actually be making use of this expression today, but I just put it there so you recognise it. And just to justify that this is makes some sense, it's interesting to consider this in the limit that x and y are very large. Then what happens then? Well, the right-hand side becomes negligible, and you get y over b is equal to plus or minus x over b, or y equals plus or minus b over a x. So you expect in the limit that there's some that it will approach a linear relationship between x and y. And you can see it in the diagram that indeed these lines are tending towards these diagonal lines. All right, but let's get back to the physics. Let's consider a special case, a physical manifestation of such an orbit. And what we have here, so what is written is that we have a comet deviated by the gravitational attraction of a planet. So here's the planet, here's the comet. This is, I meant to change this text because, well, okay, this is not strictly incorrect because it talks about a planet, but if you were to say, if this was to say a comet is deviated by the gravitational attraction of the sun, this would be a bad example because a comet is actually something in a bound orbit. A better example, and I'll try and change this for next year, is this strange entity I showed a few weeks ago, which was discovered, I think, 2 years ago, which has been given this unpronounceable Hawaiian name, which has come in from outside the solar system, has been attracted to by the sun and is now exiting the solar system again, because this is an example of something in an unbound orbit. Okay, anyway, this object, whatever it is, it will come in initially, so when it's an infinite distance away, it will have a certain velocity. It will then get attracted, bent through some angle, and come out eventually with the same velocity again. Note this quantity here, h. So this is the impact parameter. Okay, so this is some jargon. So it's easier to see what it means graphically than to describe in words, maybe. But I mean, if this object were to come in and be undeflected, then this is the perpendicular distance it has away from the attracting object. Okay. So we want to find out various things about the trajectory of this this comet, if we can call it a comet. So these are going to be the usual things, such as the minimum and maximum distance of approach. But then also we will calculate the scattering angle phi. Okay, so phi is the scattering angle, and that's the more interesting calculation. Okay. Well, firstly, let's just write down some things we know. This impact parameter is useful because it enables us to immediately calculate the angular momentum. Okay, so you can, so if you imagine this sweeping past here when it's and being undeflected, well, let's just write down J is equal to m r cross v as ever. So the magnitude of J is mvr sine gamma. You see gamma is defined like that. And when it's an infinite distance away, then r tends to then r sine gamma will just tend to h. And so the magnitude of the angular momentum is just m v0 h. Because also at this limit v is at v0. Okay. So the angular momentum is just the initial perpendicular distance multiplied by mass times its initial velocity. And clearly also E is equal to a half mv0 squared. Okay, so this is trivial. Let's now just write down the distance of closeness approach. So this, I will go over this quickly because this is a complete rehash of what we have done for the elliptical orbits. But nonetheless, let's warm up by writing this. So the total energy at any arbitrary point is given by a half m r dot squared plus j squared over 2m r squared minus alpha over r. Alpha is gmm as usual. At distance of closest approach, or perigee, we have that r dot equals 0, and we'll define that as r equals r min. So E is equal to j squared over 2m r min squared minus alpha over r min. So energy is conserved, so we put this equal to a half mv naught squared. Well, let me just not substitute this in yet. Let me just multiply through so we get the quadratic, the familiar quadratic expression. It will be we multiply through and rearrange, we'll get r min squared plus alpha over e r min minus j squared over 2me equals 0. Okay. Solve the quadratic. And we get an expression which we've had before. So it's r min equals alpha over minus alpha over 2e all into 1 minus 1 plus 2e j squared over m alpha squared a half. And by comparing this with the expression for the what we had before as the ellipse, but it was more general than that. It was just for a generic conic section. Then we can put this equivalent to the eccentricity. So let me just reiterate. This is identical to the ellipse analysis, and so is the expression. So that is why I've skipped to the result. And then we can, we know what E is, we know what J is, so we sub in for E and J, and we get that R min is equal to minus alpha over 2e 1 minus eccentricity. So this is again the same as before. So I'm just rewriting what we know already. But the key thing here is that the eccentricity is going to be greater than 1 rather than less than 1. And that is a consequence of the E, the total energy, being positive, which is different from the elliptical case. Okay, so so what we have there, therefore, the distance of closest approach. We can calculate the velocity at closest approach, and that is just through using conservation of angular momentum. Let's say the velocity at closest approach is v prime, and we know that there the angular momentum will be j equals m v prime r min. Let's just look at the diagram again to see why that should be so. So we've got the expression for this. This is the point of closest approach here. This is the perigee. So it's a distance of r min. This is clear. As the comet is sweeping past this point, it's moving entirely tangentially. So to calculate the angular momentum, we need the cross product, but the angle here is 90 degrees. So it's just r min times this velocity v prime. Okay, but this must be equal to the initial angular velocity, which is mv0h, where h is the impact parameter. So v prime is v0h over r min. Okay. Right, so now let's move on to something slightly different, which is to calculate the let's try and calculate the angle of deflection, which is phi. So here's a nice big blown up diagram, just to shall we see where, so this This is just the same as before, so this is phi, right? So it's the angle between the initial trajectory and the final trajectory. So theta is the general, theta, this is the orbital angle, which is always defined in this manner. So when the comet is here, that is theta. We can draw other angles here and here, and this is we're going to need at least one of these angles, which is what I call theta infinity, and we're going to need this because just to give you a spoiler, in a little while we're going to end up with an integral which is going to have a limits which will turn out to be these limits here. So it's probably a good idea right now to write down what theta infinity is. So this is just an exercise in Euclidean geometry by looking at this and doing an analysis and trying to see how it is related to the final angle we're interested in, which is phi. And the relationship turns out to be, theta infinity turns out to be 90 degrees plus phi over 2, or pi over 2 plus phi over 2. Now that's something you should be able to easily see yourself. It's something which I won't explain here. If you haven't convinced yourself that that is so, by the end of the lecture, come and see me, and I will show you. Right, so actually on to the physics. So what we want to do is to calculate phi. So we want to write down expressions which have phi in them. Okay. Right, so I'm going to do this actually in two ways. The first way, method one, is using the impulse. So let's scratch our head and think, well, what do we what do we know? Just coming back to the situation, I mean, what's important to understand, it starts with this velocity at infinity and it ends up with this velocity at infinity. This is an elastic interaction. So the initial momentum and the final momentum, the magnitudes of those momentums are identical. The only thing that's changed is the direction. Okay. So this immediately allows us to write this triangle which gives the change in momentum. So let's just draw the vectors. It's as drawn on the slide. So this is P initial, and this is P final. Let's be clear that P initial, the magnitude of P initial is the same as the magnitude of P final. The only difference is that the only thing that's happened is it's been moved through an angle. So there's a change of momentum here, delta P, and that's related clearly to the scattering angle. So this is phi here, but it's useful to draw two right-angled triangles, each of which has an angle there which is phi over 2. Right. So so by geometry, therefore, I can write that let's keep as vectors. So let's keep our mind on the possible signs in the problem. There's an x-axis drawn in there, and that's because in this diagram, we have defined the x-axis to point in this direction. So the consequence is that the change in the momentum is along this axis, but because of the direction the axis is defined, it happens to be negative. So this is a small detail. So dpx is just going to be given by the length of this side, which geometrically is just minus 2p sine phi over 2. And we know what p is, it's just mv0, so this is minus 2mv0 sine phi over 2. Okay, so that's already one expression involving phi, but to progress we need to get more information on what this change of momentum is. So a good way of getting that is from Newton 2, because that is force is of course the rate of change of momentum. So in this case the rate of change of momentum in the x direction is equal to the force in the x direction. Therefore the total change of momentum is going to be given by the integral of the force in the x direction over time from time equals minus infinity to plus infinity. So what is this force? Well, the force is, of course, coming from the gravitational attraction, and we know what the expression for that is. But because we're interested in the x direction, we're going to have to resolve that along this axis. So we have that delta px is equal to, just writing this again, but fx is nothing more than minus alpha over r squared. That's the gravitational attraction, but resolved along the axis, so there's a cosine theta and then dt. Okay. So progress is being made, but what is not great is that this is an integral over dt, and we're really looking at things in a geometrical manner. So we would ideally want to make an integral which is over an angle. So can we relate time and angle? Well, yes, we can. We rely on our good friend the angular momentum, which is given by mr squared theta dot, or mr squared d theta dt, and hence we can write that dt is nothing more than mr squared over j d theta. So this is great. So it means that we can rewrite the integral over time as an integral over theta. J, of course, is constant, and that's the wonderful thing about it. So let's write that. Delta px is equal to, therefore, an integral over d theta of minus alpha over r squared mr squared over j cosine theta d theta, and we need limits, and the limits now, that t equals minus infinity, theta will be minus theta infinity, and at t equals plus infinity, theta will be theta infinity. So minus theta infinity to plus theta infinity. I warned you we were going to need that. Because cosine is an even function, we can actually write this as just twice an integral from 0 to theta infinity of what we get if we simplify this, which is m alpha over j cosine theta d theta, and we still have this minus sign in front. Okay, so this is now looking quite manageable, so we can do this integral straight away. We're going to get a sine theta, and we can immediately put in the limits. So we get minus 2m alpha over j sine theta infinity. Now we know that theta infinity, I told you this at the start, is pi over 2 plus phi over 2, because ultimately we want to work in terms of phi. And so if you put this in, you will deduce that delta px is equal to minus 2m alpha over j cosine phi over 2. Okay. So this is another expression for delta px. We had the initial expression just disappearing off the top of the board. So we just equate to earlier expression. And one involves sine phi over 2, one involves cosine phi over 2. So that's going to give you a tan, or conventionally we tend to write this as a cot. So you end up with cot phi over 2 equals j v0 over alpha. You will see that from just the simple combination of the two expressions, dividing one through by the other. And this turns out to be, if you put in the expression for j, which is mhv0, so you get mhv0 squared over alpha, and alpha is g big M little m, so you end up with hv0 squared over big G big M. So this is the result for the scattering angle. I said we were going to derive this in two ways. So let's look at another way. So this is using the from considerations of the properties of the orbit. Okay, so using hyperbolic orbit parameters. So method 2. Let's look at the orbit equation. So r equals r0 over 1 plus e cosine theta. And let's consider what happens when r is very, very large. So that's the case where, you know, at t equals minus infinity or t equals plus infinity, what happens then? So if r goes to infinity, it means that that's the equivalent to saying that the denominator goes to 0. And this is, this is the case where theta is going to this, once more, this is the case where, so we're considering a big R, that's also equivalent to the case that theta is equal to theta infinity. Right, so theta infinity. So altogether this means that 1 is plus e cosine theta infinity is equal to 0. Okay, you buy that? So cosine theta infinity is equal to minus 1 over e. So this is sort of a very nice and elegant observation that this angle is directly related to the eccentricity of the orbit. as before, we want to be really dealing in terms of phi rather than theta infinity. We know that, once more, let me write it down, that theta infinity is equal to pi over 2 plus phi over 2. Okay. So sticking this in, we deduce that sine phi over 2 is equal to 1 over e. Now, with knowledge of the final expression we want to work towards, we know that we want to be dealing in terms of cot phi over 2, not sine phi over 2. So it's maybe good to already work out what cot phi over 2 will be. So this is trivially done. I mean, this is if we draw a triangle, the triangle with angle phi over 2, the right angle triangle with phi over 2. So if sine phi over 2 is 1 over e, this means that this is 1, this is e, and therefore through Pythagoras this is e squared minus 1 to the half, and hence cot phi over 2 is going to be given by adjacent over opposite, which is this over this, which is just e squared minus 1 to the half. Okay. So if we can just find a way to calculate what the eccentricity is in terms of the kinematical quantities of the orbit, then we will have an expression for the scattering angle. And we do have this relationship because it's on the top board there. Let me rewrite it here. We know that R min is equal to minus alpha over 2e 1 minus 1 plus 2e j squared over m alpha squared to the half. Sorry, running out of board here, but since this is just a repetition of this, I hope you can read it. And the reason I've written that is to remind you that it is this quantity here which is the eccentricity. So we know what the eccentricity is in terms of these quantities. Hence, cot phi over 2, I need to take this and square it, and that's okay because it's under a square root already, minus 1, so I'm just left with 2e j squared over m alpha squared, the square root thereof. So a very compact expression. I now can substitute in for, so I sub in that E equals a half mv naught squared and J equals mv naught h, and I'm left with cot phi over 2 equals v naught squared h over big G, big M, which is just the same expression as we had before. Excellent. Okay, so there's no doubt other methods we could get the same result, but I think 2 is already plenty. Let me make a final observation, which is that this was gravitational attraction, but you can consider exactly the same problem where you don't have attraction, but you have repulsion. And this is the case with Rutherford scattering, which you will recall a very, very famous experiment from the dawn of 20th century physics, where alpha particles were scattered on a thin gold foil. So what we now know is happening is that the alpha particle was being scattered by the atomic nucleus, right? And these are both positively charged. So what one gets is Coulombic repulsion. Right. So it is the formalism is absolutely identical, but we replace the gravitational potential with the Coulombic potential, and it has this positive sign, right, rather than a negative sign. And the object is being deflected rather than attracted. But the analysis of the situation is just the same, and the results that one gets are just the same. Okay? And what is a special and interesting case to note is that when phi is equal to 180 degrees, so this is when equivalent to the case where the particle is scattered right back from where it comes from, then in this case cot phi over 2, so that's cot 90, so that's cosine 90 over sine 90, so cot phi over 2 vanishes, and so this is the case where you have a head-on collision, so this is the case where h is equal to 0. So knowing what we do now, this is entirely understandable, but Rutherford and his colleagues, Marsden, this was done in Manchester, the result was absolutely astounding, because at that point they had no idea that the atomic nucleus existed. The model of the atom was that the charge was somehow homogeneously distributed through it, and Rutherford described his surprise at seeing occasions where the alpha particle came straight back as being like firing a huge artillery shell into a thin sheet of tissue paper and having it bounce back. But this was the first piece of evidence for the atomic nucleus. Okay, let us now tearfully bid farewell to orbits and move on to something else. So as expected, we're a little bit ahead of time, so we can make use of this profitably. So we'll just start this. So we're going to move on to something which will be, we're going to start a discussion of moments of inertia. A moment of inertia, we've actually introduced this already for a single particle. If you don't remember, don't worry, because we're going to define it again, but it's much more useful, and our discussion is going to be for systems of particles and eventually for extended rigid bodies. So we need to start our discussion by reminding ourselves what is the behavior of a system of particles. Okay? So this will begin with a little bit of revision from what you should have done last term. So which is, we're going to be writing down familiar things, Newton's second law and things, kinetic energy and such like for systems of particles, and show how these relationships simplify. Okay, so this I hope is a revision, but let's go through it nonetheless. Right, so the statement is that, so this is for a single body, this is just Newton's second law. and so the mass times the acceleration is going to be given by the applied force, and that can come from two sources, one which is external to the system of particles we're going to consider, and one that is internal. Okay. So now if we, because this is the expression, this is the equation of motion for a single particle I in a greater system of particles. So if we then sum over all the particles, we sum over, therefore, all the external forces, and we sum over the internal forces, and sum of over the internal forces, Fi internal, this equals 0. I mean, why does it equal 0? And that is because, if I'm considering the force between object I and J, that's going to be equal and opposite to the force between J and I. And this is from Newton's third law. So because of the equal and opposite nature of the forces between the objects, therefore the internal contribution here vanishes. And we're just left with that the this sum is equal to the sum over the external forces. It's very, very useful to deal with, to understand what's happening to the centre of mass of the system. So let's just remind ourselves how that's defined. So centre of mass of the system, that's given by RCM. So it's the sum from I equals 1 to n of mi times ri divided by the total mass of everything, where big M is, of course, the sum over the little mi's. So if we differentiate this with time, we see that the velocity of the centre of mass is equal to that dotted, which is trivially mi ri dot over big M. And we do that because we can now write that the momentum of the centre of mass, which must be given by the sum over mi times ri dot, that we can write as the sum over, I can rewrite this expression trivially as big M, little mi, ri over big M. And I do that because I can then say, aha, this is the same as what we have here. Just big M, therefore, times the velocity of the centre of mass. So these are not surprising expressions, but it's good to remind ourselves where they come from. So the momentum of the centre of mass can be written as the total mass of the system times the velocity of the centre of mass. And finally, if I want to write down the acceleration of the centre of mass, I double dot my RCM there. And that is equal to the sum over mi ri double dot over big M. And this is what we have on the left-hand side of here, so that is equal to sum over the external forces. Okay. So we have that. So I can multiply. Sorry, divided by. There's a big M there. Okay. So we have that MACM is equal to this, or if I want to write in terms of the momentum, so the momentum of the centre of mass is that, so this is also equal to the rate of change of the momentum of the centre of mass. Okay. So what we have done here is show that for a system of particles that can be expressed as a single particle of mass big M moving with or accelerating with the velocity or the acceleration of the centre of mass. So this is Newton 2 for a system of particles. Okay. So we're just warming up here because we're going to be rapidly moving towards rotational motion, but revision is not a bad thing. So now let's consider the kinetic energy. We're going to do something slightly similar. So in the lab, the kinetic energy, which we write as T, is clearly, for this system of particles, again it's a system, so it's a sum over a half m I v I squared. All right. Now let us, so the vi is the velocity in the lab. Let's write this. I mean, we can consider this as a boost into the centre of mass plus the velocity in the centre of mass. Let me write this and then comment. So this is velocity in lab. This is the velocity of the centre of mass, and this is the velocity with respect to the centre of mass frame. Okay? And this follows through a Galilean transformation, but I think it's self-evident. So I do that because I now want to write this kinetic energy in terms of these new quantities. So I have that T is the sum over half mi vi squared, which is therefore the sum over, substituting this in, a half mi vi prime squared, and the second term plus the sum over half mi v cm squared, and then I'm going to get a cross product. So plus 2 times, so the 2 will just mean that the half will vanish, but the sum over mi vi prime dot vcm. Okay? So that last term is the cross product from doing that square. But if you look at this, you can immediately say, well, that, let us just be, spell it out in words of one syllable. I can make the very trivial restatement of that by multiplying it by multiplying and dividing by big M. Let me show you what I mean. Okay, so this is so same expression. I've just divided the first part of the term by big M and multiplied the second part by big M, and I do that because what one sees now is that this is nothing more than the sum of the momentum in the centre of mass frame. So this is the sum of momenta in centre of mass, and that is of course 0. So this whole term vanishes. And we're left with the result that, so we forget about the cross product. We see what we have left, and what we have left is that T is equal to T prime plus, so T prime, this is the kinetic energy in the centre of mass. So that is the term involving the VI primes. And then this second expression, VCM is a constant. It's the same for every particle. So the sum is just over mi. And so that just gives a half big M VCM squared. Okay, so this is the KE of the centre of mass. Okay, so the kinetic energy in the lab frame therefore can be written as the kinetic energy of the centre of mass of the whole system plus the sort of the internal kinetic energy associated with the motion of the bodies with respect to each other within the centre of mass frame. So this is, these are, that should be a revision for you. These are just for translational motion. What we will do next, which will be on Monday morning, is then immediately make the switch to looking at what these quantities appear as for rotational motion, and that will rapidly lead us on to the concept and the need for the moment of inertia for an extended system of particles. So see you next week.